Oh, that's the K, I'm sorry, kappa times epsilon sub naught. Get rid of the charge. I'm sorry. Oh, divided by the distance.
Multiply times the area and you have the capacitance for the electric field. This was in test 1A, wasn't it? Yeah, that was test 1A. Figured you would have done test corrections by now, or at least look at it.
Give my best guess. Oh.
The surface charge density divided by epsilon sub naught.
That's right.
Ringing a bell, I hope.
Yeah.
Got a couple of nods and a couple of I'm about to fall asleep.
No, I'm not, I promise I'm not.
Okay.
I was just scratching my face.
What is sigma? Well, how would you find sigma?
The density.
Okay, yeah, that's what it is. How would you find it?
Divided by area.
There we go.
Yeah.
All right, so that's Q over epsilon sub naught times area. I'm assuming there's nothing in between the plates. So if I looked at the change in my electric field over the change in time, that would just be the change, well, the area is not changing, my permittivity is not changing, so the only thing that would change is the amount of charge that's showing up on the plates. So that would be the change in the amount of charge on the plates over time times 1 over epsilon sub naught A. And what is change in charge over change in time? Say it like you mean it.
Current.
Yeah, there we go.
Nice.
But it's not the same type of current that we're dealing with, because I have charge coming on, but it's not like there's charge leaving right there. And so we put a little subscript D here. This is the charge because we just have, the current, because we have this change in charge on the plate, and this is known as displacement current. If I multiply both sides times, well, let's get rid of this. Let's get displacement current all by itself. So I sub D, my displacement current, is just going to be, well, multiply both sides by that denominator. So I get epsilon sub naught A times the change in my electric field over change in time. And again, this E is the magnitude of my electric field. It's not energy. My area is a constant. I'm just going to bring it into the fold here. So this is epsilon sub naught times the change in EA over delta T. And what is the electric field times the area?
Electric flux.
So this becomes epsilon sub naught times the change in my electric flux over the change in time. I know, you're thinking, that's just incredible. Yep, it's like I'm reading your mind. Let's take a look at Ampere's law. Ampere said that if I look at the magnetic field over a length through a closed loop, that's going to be equal to mu sub naught times I. We'll just actually put the 0 in there. Maxwell comes along, he does this, goes through this bit, more sophisticated, but goes through this bit and says, well, actually, we've got two currents involved here. We've got the traditional current dealing with charge flowing past a certain point, and then we have this displacement current. And so what Maxwell does is he separates them. We have the normal current that we've been dealing with, and then we have this new kind of current. So that's equal to mu sub naught times the normal current plus mu sub naught times epsilon sub naught times the change in the electric flux over the change in time. Ampere's law with the Maxwell correction. The implications of this are incredible. You take this in combination with Faraday-Lenz's law, where we have this EMF, and EMF is just a voltage that's equal to the negative electric field dot delta x, L, whatever we're talking about, x, is equal to negative change in magnetic field over change in time. Now, I'd be shocked if you suddenly see all the implications of it at this point, but I'll give you a shot. What are the implications? I shouldn't have set it up with, I said I'd be shocked if you knew it and just let it out there, but oh well. If I take a charge here, Q, and I move it over to here, all I've done is I have a charge and I move it. It is giving off some electric field at this point. And when I move it over to here, it gives off an electric field at this point. So if it's sitting at this point right here, looking, just watching this charge move, well, my electric field at where I am goes from this to that. My electric field changes. If my electric field changes, then I have a change in electric flux going through me. If I have a change in my electric flux, that's going to create a magnetic field. So I have a change in the magnetic field. If I have a change in a magnetic field, so basically it creates a magnetic field, so it goes from 0 to something. So my magnetic field changes. My magnetic field changes, that means the magnetic flux changes. Magnetic flux changing is going to create a voltage, or in essence, it's going to create an electric field. So by changing an electric field, I can create another electric field. Now I take this charge and I keep just oscillate it back and forth. So my electric field is constantly changing. So the implication, I have a change in electric field, which creates a magnetic field. If I change my change in electric field, so just oscillating back and forth, I'm going to change my magnetic field. Change in my magnetic field is going to create an electric field. So if I change the change of the change, that's going to create a change in the change, which creates a change in the electric field, which basically creates a magnetic field. And if I can keep this thing oscillating back and forth, I create this self-perpetuating thing, where I constantly have an electric field and a magnetic field creating each other. Maxwell's next step was to figure out, all right, I got something that's now creating itself. I got these two fields that are moving along. How fast are they moving? We'll do the derivation later. But he calculates that the speed of this electromagnetic wave is 1 over the square root of u sub naught times epsilon sub naught. You've got a calculator, pull it out. That's 1 over the square root of 4 pi times 10 to the negative 7th times 8.85 times 10 to the 12th. Sorry, negative 12th.
What was the first superscript? Negative fifth?
Here, where are you looking?
Yeah, right there.
That's negative 7.
Is it a really large number?
What do you get?
We'll call it 3.0 times 10 to the positive 5, 6, 7, 8. Oh, that's the speed of light.
Ah! Maxwell comes out with a calculation of an electromagnetic wave, comes out with a number so incredibly close to the speed of light that he concludes, I don't know if light is an electromagnetic wave, but it seems too much of a coincidence that the speed of an electromagnetic wave is the same as the speed of light. They found the speed of light experimentally at this point, just by bouncing off a bunch of mirrors. So that, more sophisticated than that, but that's the essence of it. Now, Physicists looked at this. He came up with this formula here. Physicists very quickly agreed that light is an electromagnetic wave, but then some group of physicists, matter of fact, most of them said there's a mistake. What is the mistake that physicists incorrectly assumed at that time? They had absolutely nothing wrong with what his derivation was, but there's something clearly wrong with this, according to, I think Lorentz was one of the big guys. Lorentz was probably one of the biggest advocates. He jumped through hoops trying to justify why what he claimed should have been in the formula is not there. And this goes back to the nature of what speed is. Flashback to the beginning of 151.
Speed doesn't have, isn't a vector. It doesn't have direction.
Okay, not the issue here. I mean, the direction that we can turn this into a velocity. So that was not the issue they were having. Sorry, I think I came across far more harsher than I meant to.
You're fine, no, you're fine, you're fine.
I think we're used to being rejected by.
No big deal, no big deal.
Does it have to do with time and the seconds? Like, I'm not really sure where seconds came from in this part.
If you worked out the units of these two things, the seconds come out. The units actually are fine. What is the nature? What is speed?
Displacement, speed is distance over time.
Okay. So how fast are you moving right now?
0 meters per second.
Is he right?
Yes,
Are
I'm
we
right.
not factoring the rotation of the Earth?
Oh, are we? Were you?
I was not.
Is he wrong?
Well, it depends on your point of
Yes,
reference.
yes, I know.
Where's the point of reference in this? This is an absolute number. U sub naught and epsilon sub naught are not dependent upon a reference frame. Those are supposedly these constants. And so the physics community said, excellent work. He ultimately gets a Nobel Prize, deservedly. Although it'd be 25 years because the Nobel Prize hadn't been created yet. But there's no accounting for reference frame. And the person who comes along and says, he's not wrong, there is no reference frame here, the speed of light is the same, regardless of the reference frame. Einstein. Think about the implications of this, of the fact that there is no reference frame here, and that's light. If I am, sorry, we're about to get into the really cool stuff here. I want to leave if you're okay with it, I want to take it to the last step here, just so that your mind gets blown slightly before you leave.
Go ahead.
All right. I have an experiment here where I have a box that's going to, and a mirror up here, a mirrored ceiling. It's going to shine a light up, and the light's going to hit the mirror and bounce back. This thing is going to be moving to the right at some speed v. The light, therefore, will have a sideways component to it, and so the light is basically going to bounce there and then be picked up by the box as it moves past over here. So in the lab frame, that's what you would see. You're standing here, you see the thing go by, light comes up, bounces back. In the reference frame of the box. So you're in the box, all you would see is the light go up and come back. The whole lab is moving off that way, but you don't care about that. You just care about you're in the box, you see the light come up, comes back. If the speed that the light travels, in this case and in this case, is the same, which is what that would imply. So if the speed of light is the same, and let's just go ahead and use the letter C for that, since that's what's traditionally used for the speed of light. In which reference frame does the light travel a greater distance? Not a trick question.
It should be equal.
Why? If I see something bounce up and hit the ceiling and you see it go over there and then go over there,
You would think it'd be the one that goes way over there.
Yeah.
yeah, so the light's traveling farther here. If the speed of the light is the same in both cases, and this is a bigger distance, what else is different between these two?
Time.
Tom,
And so the implication of there being no reference frame here, if that is true, then time is not the same. And that was one of those tenets of physics, and actually life, is that the time is the same for everybody. 1 hour is the same as 1 hour everywhere. And now Einstein comes along and he says, no, time is not the same everywhere. Einstein figures this out. 1905 is when the paper gets published, along with his first basis of general relativity and the idea of uses statistical analysis to show that air is made up of particles. There was a fourth paper he did that same year, but any one of those three actually were worthy of a Nobel Prize. He ultimately, Einstein wins it for contributions to physics, just because, well, frankly, there was prejudice against him because he was Jewish. Nazi Germany did not pop up out of a vacuum. But at some point, they could not deny him anymore. The proof would finally show up in the mid-40s, early 40s, I think just before we entered World War War II. That's the first bit of evidence to actually show that time is not the same. But that will be for another day. I have tests, if you want them back.
That was a doozy.
And thank you for your patience. Oh, and before I accidentally flash something, stop this.